Good morning, all my dear students. Welcome to the another topic in the Unit 1, the elements of the first transition series. Now, in this lecture, we should talk about the first transition series or the 3D series. We have discussed in the previous lecture the transition elements, the classification of the transition elements, the different characteristics and the properties of the transition elements. Now we talk about each one of the series in the detail. So in this lecture, we should learn about the first series of the transition elements, that is 3D series. These are the prerequisites required for this lecture. The students should have the knowledge about the transition elements, its classification, the characteristics of the transition elements, and the properties of the transition elements along with its trend in the periodic table. In this lecture, we should cover the following contents: the introduction of the elements of the first transition series, that is 3D series, the characteristics of the first transition series like electronic configuration, oxidation state, the complex tendency, formation of the colored ions, catalytic activity, formation of interstitial compounds, metallic character, alloy formation, and periodic properties like atomic radii, ionic radii, melting point, boiling point. What is the learning outcome of this lecture? The students will be able to understand about all the characteristics and the periodic properties of the first transition series, which contain 10 elements. So the first transition series, which is also known as 3D series. Why it is called 3D series? It is because the last or differentiating electron in the atom of these elements enter in the 3D subshell. As we have classified the transition elements into the 4 series, the 3D series, 4D series, 5D and 6D. And 3D series starts from the scandium, which is having the atomic number 21 and it is of the group 3. It ends at the zinc, the element of the group 12. So total number of the elements in this series is 10. This series lies in between the calcium and the gallium. So calcium comes in the S block element and the gallium is in P block element. So these all 10 elements lies between the calcium and gallium. The elements of group 2 and group 13, the group 2 is of calcium and group 13 is of gallium. The 10 elements of the first transition series, as you know, the 21 atomic number, that is scandium, then we have titanium, okay, then vanadium, chromium, manganese, having the atomic number 25, then iron, cobalt, nickel, copper and zinc. Understood? These elements are much more important than those of the second transition series. All the characteristics and the property of the D block elements should be shown in this lecture of this first transition series. So we will talk about these all 10 elements and their properties in this lecture. First, we talk about the electronic configuration. So as we see, the electronic configuration of the 3D series is 3dx 4xy, where x is 1 to 10. 3D range of the electron come to 1 to 10, and y is the s, which is having 1 or 2. The 3D subshell has 1 to 10 electron from scandium to zinc, and 4s subshell is generally having the 2 electron, except the chromium and copper. The chromium, here you can see here the chromium electronic configuration, which is having 3d54s1. Okay, and copper is 3d10 4s1. So 3d54s1, 3d10 4s1. Excluding both these elements, all the elements in the 3D series is having 4s2. The exceptional valence shell configuration of chromium and copper is due to the exchanged energy effect and extra stability of half-filled and completely filled subshell. Because of this stability, they are having this electronic configuration. The shifting of an electron from one subshell to the another of the similar or slightly higher energy in order to achieve the half-filled or completely filled subshell. So that is called the exchange energy effect. So the electron shifts from the S subshell to the D subshell, and having the half-filled and the completely filled subshell, which acquire the stability. So due to that, the chromium and the copper has the electronic configuration, okay, and rest of the elements is having the 4s2. The second characteristic is the oxidation state. Transition elements show the variable oxidation state. Variable means many, and it can be observed in their compounds, in their ionic forms. So the cause of showing the different oxidation state of these elements having the 3D electrons, which are quite closer to the 4s electron in the energy. So it can easily form the bond and form the compounds. The minimum oxidation state shown by all the element is +2, except the copper and the chromium. The +1 is also observing in the copper as well as it is in the chromium. And you can see here the oxidation state goes on increasing till the middle of the element, that is manganese, and then it starts decreasing up to the zinc. So it increases from scandium to manganese and decreases till zinc. The maximum number of the oxidation state we can see here +1 to +6 or +2 to +7. From scandium to the manganese, the highest oxidation state is shown by the elements, and +2 and +3 oxidation state is dominating in the first transition series. Many of the elements is having +2 and the +3 oxidation states. It has also been observed that the first transition series form the ionic oxides and chlorides in the lower oxidation state, which are basic in nature. As the oxidation state increases, the covalent character and the acidic nature also increases. So the oxidation state increases, the properties of the compound also differs, as in the lower oxidation state it forms the basic oxides and having the ionic bonds, but as the oxidation state increases, the covalent character and the acidic nature increases. As you can see, the manganese oxide, which is +2, which is basic, but Mn2O3, MnO2 +3 and +4 are amphoteric, and the highest oxidation state, that is of manganese oxide, which is acidic. Similarly, we can have the example of chromium also. Chromium oxide, which is basic, then when it increases is Cr2O3, that is +3, which is amphoteric, and then it increases to +6, that is acidic. So from it all nature you can understand, as higher oxidation state, the acidic character is going to increase. The complex tendency is one of the important characteristics of the transition elements, and the elements of the first transition series fulfill all the conditions for the complex formation and most suitable. For this purpose, the cations of these elements having the strong tendency to form the complex with the neutral molecules like carbon monoxide, nitrogen oxide, ammonia, and several ions, highly electronegative atom, fluoride, chloride, cyanide. These molecules called ligands, which have one or more lone pair of the electrons, that are donor atoms, which they donate to the metal ion, that is cation, during the process of complex formation. So ligand always donate the electron to the metal ion. Here M is the metal ion and L is abbreviating as the ligand. And this type of the bond is called coordinate covalent bond. So the complex formation in a detail we study in the coordination chemistry. This happens because the metal ions are electron deficient. In most of the oxidation state, even the atoms are electron acceptors. Due to the small size and high charge density of the metal ion, it facilitates the formation of complexes, which also depend on the basicity of the ligand. The complex formation tendency increases as the positive oxidation state of the metal ion increases, because the positive oxidation state causes the smaller size, high charge density. Okay, so this favors the formation of the complex. So as small size of the cation is there, can easily form the complex. The nature of the complex depend on the orbitals available on the metal ion or atom for bonding. The orbitals we know that S, P, D, and the structures of commonly found in the complexes of the first transition series, that is linear. Okay, we have linear complexes formed by the first transition series, square, planar, tetrahedral, octahedral. This shows that the metal orbitals are hybridized before bonding with the ligand orbitals. So this is an example of nickel complex, which is square planar, and nickel chloride, which is tetrahedral. So it depends on the nature of the ligand. Here the ligand is cyanide and here the ligand is chloride. So depending on the nature of the ligand, if the strong ligand is there, weak ligand is there, so we have the different complexes form. So same metal ion, the transition metal nickel, form different type of the complex. You can see here that is square planar and tetrahedral. Formation of the colored ions. The elements of the first transition series form the colored ions or the compound or the complex, which is due to the presence of unpaired electron. Let's see the example. We have the cobalt complex, which is pink color. And if we talk about the copper ions and its complex, we see the cuprous ion. It is having the completely filled D subshell. This cuprous ion and its salts are colorless due to this completely filled D subshell. It is not having the unpaired electron. But cupric ion, which is having the unpaired electron, and its compounds are colored. That is copper sulfate. You have seen in the lab, that is blue color, which is actually represented by this. And the copper, again the complex with the ammonia, it is a dark blue, which is almost violet. We have other examples also. Nickel, we have the complex which is this red in color when it forms with the ammonia, which is blue in color. Among the other compound, we have vanadium oxide, which is pale yellow, the chromate, strongly yellow. This is the manganese oxide, which is purple in color, the titanium, green color. You have all the complex or the ions. These are all the example of the first transition series which are colored. So it is due to the presence of the unpaired electron. The color of the complex depend on the nature of the ligands and the type of the complex formed. The metal ion which completely empty or completely filled are colorless. We have seen the example of that is cuprous ion, which is having the completely filled D subshell 10. So that is colorless. So if we talk about this scandium 3 positive, this is empty filled 3D0. If we talk about titanium 4 plus oxidation state, that is also the empty D subshell. Here you can see the cuprous ion, what I have said earlier, zinc. So these all the ions or the complex in which having the filled D subshell, empty D subshell are colorless, and rest having the unpaired electron are colored. The catalytic activity of the first transition series. The elements of the first transition series and their compound have been used in the industrial process. Their availability in variety of the oxidation state makes them capable of forming the intermediate products with the various reactant and the tendency to form interstitial compound which can absorb and activate the reacting species and act as a catalyst. We have seen the transition elements due to the variable oxidation state. It has the capability to form the intermediate compound. So it can easily absorb over the reacting species and act as the catalyst, lower the activation energy. In first transition, see the finely divided nickel, which is used as the catalyst in the hydrogenation reaction, where we convert the oil into the fat. The hydrogenation process is the formation of the fat from the oil, and there the finely divided nickel is used as the catalyst. Manganese oxide catalyzes the decomposition of hydrogen peroxide. Titanium chloride as a catalyst for polymerization of ethene in the manufacture of polythene in the polymers. Vanadium oxide is employed in the catalytic oxidation of sulfur dioxide to sulfur trioxide. And again, an important catalyst, iron, which is used in the manufacturing of the ammonia in the Haber's process. The copper is also act as a catalyst in the manufacture or the synthesis of the silicons. The large-scale production of the nylon 6 is where the copper and the vanadium is used. The ferric ions catalyze the reaction between iodide and peroxo disulfide ion. So several industrial processes in the large manufacturing of the products. The first transition series elements show the catalytic property. The another important characteristic of the transition element is the formation of interstitial and the non-stoichiometric compound. Elements of the 3D series are capable of forming the interstitial compound like titanium carbide, vanadium carbide, scandium nitride. These compounds have the properties of the alloy, being hard and good conductors. These elements also form the non-stoichiometric compound. The titanium forms the titanium oxide, where the X can be the 0.65 to 1.25 or 1.98 to 2.00. So it can have this range: manganese oxide, vanadium oxide, which is having the range. These compounds have variable composition. Their proportions varies and are formed due to the variability of oxidation state and due to the solid defects. Okay, we have talked about the various solid defects when in the preparation of the compounds. It generally causes such defects. It acquires the position of the interstitial space between the lattice, and due to this non-stoichiometric compounds are formed and interstitial compounds are formed by the transition elements. Metallic character and the alloy formation. The metals of the first transition series are hard, malleable and ductile. All are having the metal property, and these exhibit various FCC body-centered, cubic and hexagonal close-packed lattice structures. These metals are good conductors of heat and electricity. Copper and the metal of iron tride are softer than the other metals. And the alloys are also common of this series. You all know that is brass, which is an alloy of copper and zinc. Nichrome, that is used as a wire. Nickel and chromium. Monel matter, that is copper and nickel. German silver, copper, nickel, zinc. Stainless steel, iron, chromium, nickel, manganese. Variety of the steels are there according to the proportions. These alloys are harder and having high melting point than the parent metals. They are also more resistant to the corrosion and their constituents. So they are having more good properties, the engineering properties like hardness, its strength, melting point, boiling point from the parent material. The periodic properties and their trend of the first transition series, we talk about these important periodic properties, atomic and ionic radii of this series, melting point and boiling point, ionization energy and the reactivity, the reducing property, the standard electrode potential. If we see the atomic radii, and we all know along the period atomic radii goes on decreasing with the nuclear charge increasing. Here you can see the values of the atomic radii of the first transition series, and you can see here that atomic radii goes on decreasing up to nickel, and then slight increase shown by the copper, and more high it is shown by the zinc. So we can say the values goes on decreasing up to the nickel, that is the normal thing, but increase slightly for the copper but pronouncedly for the zinc. And zinc has the exceptional value only lower than those of the first two elements and higher than the other. So due to the extra stability of the zinc, and we have the copper also, due to that the atomic radii is higher of the zinc. Let's talk about the ionic radii of these elements. Follow the same trend as the atomic radii. With the value you can see the ionic radii with some charge generally goes on decreasing except for the last element. So here you can see the ionic radii value 95, 90, 88 goes on decreasing, but here again we have an increase in zinc. It is shown in the bivalent ions, and here for the trivalent ions we can see here it goes on decreasing. So let's see the melting point and the boiling point of the first transition elements, which is generally high, but they are irregular trend we can observe here. The highest melting point is of vanadium, and the lowest melting point is of zinc. Okay, you can see here the vanadium is having the higher melting point, and zinc which is having the low melting point, and other element manganese and copper having the lower melting points as compared to the members. The boiling points are also very high except for the zinc, which is to be expected, that is for the stability. The ionization energy and the reactivity of the first transition series. The first ionization value of the 3D series is showing the irregular trend, but the second and the third ionization energy generally show the increasing trend from scandium to the zinc. Here you can see the value of increasing order of the ionization energy in kilojoules. From scandium it goes on increasing, and which is having the higher ionization energy, that is 906, that is of zinc. This is of zinc. 906 is the ionization energy is of zinc, and it is due to the additional stability associated with the completely 3D suction. But the variation of the ionization energy, the first ionization energy irregularity, is due to the change in the atomic radii, and because of the screening effect of the extra electron added in the 3D subshell. So as goes on along the period, the screening effect increases, which exerted on the nuclear charge. So due to the change in this screening effect increases, the change in the atomic radii, we have the ionization energy also changes. The standard reduction potential of the 3D series, except the copper, it is lower than the standard hydrogen electrode, means they have the lower electrode potential, and these elements evolve the hydrogen from the acids at a very low rate. It can easily evolve out the hydrogen. Copper does not react with the acid, and it has the tendency to reduce. Sometimes the metal are protected from the attack of the acid by the thin layer of the inert oxide. For example, chromium. These metals are oxidized easily to their ions and hence the reducing agent, though almost poor. So here you can see the electrode potential of it is that is lower than the hydrogen up to the nickel, and copper only instead of copper lies above the hydrogen, and zinc is also having the lower potential to the hydrogen. So they have the lower electron potential, so they have a tendency for the oxidation. So these all are the important characteristics and the properties of the first transition series individually, with the periodic properties and the important characteristics. In the next lecture, we talk about the binary compounds of the first transition series, which type of the binary compound it forms, what are its different properties and its uses. These are the references. Thank you and take care.